My name is Vidur, and today we'll be seeing a lesson on regression theory, and we'll be focusing our efforts mostly on linear regression. Right? Let me first introduce myself. My name is Vidur Walia, and I have a background of uh, master's in statistics from Delhi University. And right now, I'm working as a data analyst and a multinational company. Right? So, without any further ado, let me share my screen, and then let's get started with the lesson. So basically, regression is a statistical technique which is used to predict an outcome variable, right? Which is usually termed as the y variable. You must have heard about it, right? With a given set of independent variables, which are usually denoted by x. Now, these x could be a number of variables or a single variable. Right? In this lesson, we'll be starting first with the simple linear regression in which the explanatory variables, the x variables, see the x variables are also known as explanatory variables, right? And y is obviously the outcome variable, right? So in simple linear regression, we just have a single value for x, a single variable x, but in multiple linear regression, which is the next step to simple linear regression, we get multiple values of x, right? Let's go forward. Let's take an example. For example, we might be interested in predicting the sales of ice cream, right? Predicting sales of ice cream in dollar values, and the input variables or the dependent variables that might be affecting this could be temperature that day, temperature of the day, right? It could be whether or not uh, it, um, it is a holiday season or not, right? We expect that if it is a holiday season that the sales of ice cream would be more, right? If the temperature of the day is higher, we expect uh, the sales of ice cream to be higher that day for obvious reasons, right? Another variable that we can think about, it could be rainfall. This would be an inverse kind of a relationship. If rainfall rises, then the sales of ice cream should be falling, right? So in order to predict, and we can see that all of these variables intuitively make sense, right? These also, if you can obviously, the price of ice cream at that time is a major variable, right? And let me give you an industry example as well. When we are trying to model these variables, when we are trying to predict the sales or outcomes, price is one of the most important variables for any packaged product or for any economic product that we are buying, right? These might be secondary variables, but price and how much ice cream as a manufacturer I'm already keeping in my stores, which is also known as distribution. So these are the two variables. Let me just write it down over here. Distribution. Distribution means how well I am distributing my product in the stores. So obviously, if I have more products in my stores, my sales, it becomes more probable for me to, sell more ice cream. For example, if you go to a store and if you don't find brand A for the ice cream, you won't be able to buy it, right? So these are the two main factors which are affecting the sales of ice creams. And along with these three factors as well, there could be some more factors as well which can affect the sales of ice cream. So all of these combined are the x variables or the dependent variables. Now we can call price as x1, distribution as x2, this as x3, x4, x5. So now we know that these are 5 variables that I have taken, right? I have some data for these 5 variables, and I also have the data for ice cream sales for these variables, right? For example, the data that you might be having could look something like this. Or let me just go down in the basic understanding itself. I can write it down. Example data set. So I have x1, x2, x3, x4, and x5, and this is the y variable, right? So for example, I get 500 units of ice cream sold when price was suppose 10 rupees. Distribution, let me keep distribution as 20 this time, right? I'll create just 5 rows quickly, or let's create just 4 rows. 25, 15, again 20, right? Let's take price as 9 rupees, let's take price as 10 rupees, and let's take price as 8 rupees. Then temperature of the day could be 25 degrees Celsius, 30, 32, 34. Holiday season is yes. Yes stands for, 1 stands for yes, and 0 I'm denoting as no as of now, right? Then I have rainfall. Rainfall is usually measured in millimeters. Let's say 20 mm, 15 mm, 10 mm, 5 mm, right? Now, based upon these values, we know that the price would obviously have a inverse relationship. So I'm putting a downward arrow over here, which means that as and when the price rises, the outcomes, the outcome, that is the units sold, would become less, because if ice cream becomes expensive, we tend to buy it less, right? Distribution will have a, yes, positive relationship. X3 is my temperature of the day, would also have a positive relationship. As soon as the temperature rises, the sales of ice cream would rise. X4 is holiday season, again rising. X5 is rainfall, decrease, right? So this is just a random data that I am predicting. And since we already have taken this understanding, this market experience with us, that price and distribution are more important. As price falls and as distribution rises, right? Again, temperature is also rising. Let's say that the temperature, even if the temperature falls a little bit, let's say the temperature fell to 23, right? Then also I would expect my ice cream sales to be a little high, right? And we can write this data set. So this is the kind of data set that we would be having, right? Now, obviously, this is a sample data, okay? Because we cannot measure all the ice cream sold all around the world, but we will always have a sample data, right? Now, once we have the understanding of this data, we have already seen what a bivariate analysis is. Let me just draw a quick graphical representation for us so that we can understand this. So linear regression is basically now predicting these y values with the given x values that we have. And why is it called linear? Because we are expecting that there is a linear relationship between x's and y. So basically a linear combination of x. What do I mean by linear combination of x? Okay, I'll just get to that in a minute. Let's just quickly get over with bivariate analysis graphs. Okay, let me just draw. I never seem to draw this correctly. Let me just draw it by hand. Right? Bivariate. Bivariate means two variables. One is obviously a y variable, which is represented on the y-axis very conveniently, and the other one would be an x variable. Right? Let us consider that in this case, let us consider we only have this x1 and y with us. Just consider this for a moment. Right? There could be 3 scenarios. The first scenario could be just like this x1, that as x rises, y tends to fall a little bit. We could have these data points, right? Now each dot represents some value on the x-axis, and some value on the y-axis. But if we see an overall trend, we'll be able to see that it's somewhat going downwards, right? This is an inverse relation, correct? Then suppose we just have x2 and y with us, distribution and sales. If the data looks something like this, overall we can see that we have an increasing trend over here. As x rises, y rises. As x falls, y falls. So this is called a direct relationship. Now you must have heard about correlations. Correlation would be greater than zero, that is positive. Oh, sorry, negative correlation. Correlation would be negative over here. Since there's an inverse relationship, correlation has to be less than zero. Here, my correlation has to be greater than zero. And suppose the data does not seem to be affected. The y values do not seem to be affected with x. Then we can say that the correlation is almost zero, right? But we have to understand this, that we are saying here that when correlation is zero, when correlation is zero is equal to zero, it does not mean that there is no relationship between the variables, but it means that there is no linear relationship. Linear relationship between the variables. So what it means is simply that correlation is a measure of linear relationship among the variables. So obviously this is a bivariate analysis. We have an x value, that is the dependent variable, that is the independent variable, and y, that is the dependent, because y is dependent on x. Outcome variable with a set of independent variables. Sorry, ma'am. Independent variables. Let's move on further. Now, since we discussed that we are describing a linear relationship, and I just now told you that let us assume that we only have single variables at a time to understand this bivariate analysis. But what if we have a combination of all of these together, right? On a 2D graph, obviously we can just have two variables. One of them would have to be the target variable y, and we only have another axis left with us over here to represent any one of these variables. But if we start thinking in a higher dimension, let's start thinking in 3 dimensions. Just look at the room around you. And have you ever seen a rope on which we are hanging clothes to dry out? Don't you see that that is a line in 3 dimensions? So a line can exist in more than 2 dimensions as well, right? So even if we have these multiple variables, x1, x2, x3, x4, and x5, we can have a line passing through a room using those in 5 dimensions. But leaving that aside, there is one more way that we can do that. Let's see. Suppose we create a linear combination. Now, what is a linear combination? Suppose we have x1, x2, x3, x4 till x5. Let me tell you what a linear combination is. So suppose a is a coefficient, ax1, multiplication of this value, this a value times your x1 variable plus b times your x2 plus dot 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 plus maybe e times your x5, a, b, c, d, e, right? So this consists of a linear combination. Now we can see this as the independent value, which could be used to predict your y variable, right? If we have a single value of x, like in simple linear regression, we might have ax from which we are trying to predict the y variable. Now it becomes very evident and very clear that if we have this value of this coefficient a, or if we have value of these coefficients a, b, c, d, and e, our main task is done. We can try to fit this line and we can have an estimate of y using all these variables, right? So in order for us to understand this better, for theoretical purposes, let us take the case of simple linear regression first, right? Let me just create a scatter plot here. Suppose this, now I'm deliberately drawing some points so that you can see a clear trend going upwards, right? It's a very clear trend that a line that goes in this direction could have a good fit over here. Now we are considering only one x variable regressed for a single y variable, obviously. So for a y variable, we have just a single x variable that is to be regressed, right? Let me write y over here and obviously x over here. Now, if you imagine, you must have also learned in school that the equation of a line is y is equal to mx plus c, which means that a line can be defined by only two parameters. A line can be fully defined by these two parameters. This m is called the slope and the c is called the intercept. Now in statistical terms, what we can write down is, now let's see, just keep in mind this equation, and now let me give you the equation of linear regression. Right? The equation of linear regression is y is equal to, this is the Greek letter beta with subscript 0, also known as beta naught. Beta naught plus beta 1 x plus epsilon. Right? Now you might be able to see some analogy from here to here. Now we can obviously see that the c-intercept here becomes beta naught. The slope coefficient here becomes beta 1, right? So these two things are clear to us. And now we are trying to fit this line, consider only this part as of now, right? We are trying to fit this line on these data points, correct? So obviously this is a line, the dotted line that I have drawn. It has to be of the form y equal to beta naught plus beta 1 x. But why have I put this epsilon over here? This epsilon is known as the error term. And what is the error term? If you look very carefully over here, you will see that these points, y value actually refers to the y coordinate of these points. These points do not directly lie on the line. Now the line is doing a good job of estimating the overall area where these guys are present, these points are present. But obviously, for example, let me just show you, add a gray color, small size pen. Just see this. Can you see this distance of this point, the distance of these points from this line, right? These are the error terms, right? Because obviously in real life data, we cannot find a data which is exactly linear unless it is a linear function of some other variable. We are trying to predict y basis this x value, assuming that a line is a good fit. Now, line is a good fit as we can see here, but line cannot 100% accurately predict this. But we are okay with that. That's not a problem. We are trying to estimate the values of y for future periods, right? So that is why our linear regression equation looks something like this. So y is equal to beta naught plus beta 1x plus the error terms. And our main goal is to predict this beta naught and this beta 1. Now you might argue, the next question that might come up could be that how do we know that this is the line to go for? Why can't this be a good fit? Why can't this be a good fit? Obviously, these lines can also be a good fit. Now, just by eye sighting this, we can make a rough line. But how to know for sure that the line that we have drawn is the most accurate and the best fit? There comes the next challenge, right? We have already done the equation of line. The line of, let's see what the line of best fit is. Now we have already seen over here that there can be multiple lines that can be drawn over a particular data set, right? And just now we saw that this is the error term. Now our hint comes from here. What could be our motivation to find the line of best fit? We can easily define the line of best fit as that the line of best fit is the line which produces least amount of error over the given data set, right? Now, obviously, if you just try to inculcate or try to aggregate these errors for these three different lines. Now, since these are three different lines, for each point, I will get three different errors, right? One from line 1, one from line 2, and one from line 3. Now, you might think that it is good for us to add up these errors and then see where the sum of these errors is the minimum. That is a good thought. But did you notice that some of the errors are positive? That is, some of the points lie above the line and some of the points would lie below the line, right? So these positive and negative errors might cancel each other out and we might not get a clearer picture over here, right? So what do we do next? Now, slowly we are progressing into the theory, right? We are taking logic and we are trying to build up the theory of how do we find the ideal values of beta naught and beta 1, because obviously all these three lines have some equation, m1x plus c1, m2x plus c2, m3x plus c3, because these are three different lines. So the best value of m and c, or in statistical terms beta naught and beta 1, which produce the least amount of error, will finally give me the line of best fit. And now we are getting into the techniques of how to get these values. Right? So here comes the catch. We understood that we cannot do the sum of errors, right? If we do the sum of epsilon I goes from 1 to n, this is the sign of summation. That means epsilon 1 plus epsilon 2 plus epsilon 3, basically adding up all the errors for a single line. In this, the error is positive and negative errors cancel each other out, right? Okay, what else could be done? Someone might suggest that we could take the absolute value of epsilon 1 plus epsilon 2 absolute value, epsilon 3, and so on and so forth. In this way, the negative and positive values will not cancel each other out. But consider this proposition. I take epsilon 1 square plus epsilon 2 square plus epsilon n square. So instead of taking a modulus, I'm taking a square, which can also be translated as sum of epsilon I square. I goes from 1 to n. And this is squared errors. Now, there's a very good reason that I'm not going uh, towards the absolute value of errors and I'm taking the sum of squares. And I'll just get to that in the next section, that is method of least squares. OLS stands for ordinary least squares, right? OLS is a technique through which we find the value of beta naught and beta 1. Okay, all right. Now let's see. We have sum of epsilon I errors, right? And if I write y is equal to, let me write yi because we can do that for each value. Beta naught remains constant. Beta 1 remains constant because these are parameters. These are population parameters that we are trying to estimate. And parameters are fixed statistical values which do not change, right? Multiply with xi plus epsilon I. This implies epsilon i's value becomes yi minus beta naught plus beta 1 xi. Now remember that these are yi's value. Yi's and xi's are the values that we already have over here, right? We already have them in our data set over here. Okay. And let me calculate epsilon I square over here. So what will I get? I will get yi minus beta naught minus, this should be minus beta naught minus beta 1 xi whole square, right? And what is my main aim? My main aim is to reduce the total errors. So if I take sum on both the sides, taking sum, I get sum of epsilon I square is equal to the sum of, obviously over I yi minus beta naught minus beta 1 xi whole square. And this is exactly what I got over here. Remember, I still haven't given you a reason for why I'm not taking the absolute values here. Just bear with me for a minute. I'm just coming to that. In statistical lingo, this sum of epsilon I squares is called the sum of squared errors. And my main objective is to minimize this. Do you remember from your class 11th and 12th that minimization, that if I minimize the sum of squared errors, basically I'm minimizing the errors only, right? Albeit squared. If you are trying to minimize the square of something, obviously that value would also minimize, right? And do you remember in the chapter of derivatives, to minimize something, we need to take the derivatives. So if I take the derivative of summation of epsilon I square with beta naught, and I take the derivative of summation of epsilon I square with beta 1. I take the derivative, equate it to 0, and then try to find the value of beta naught and beta 1 for which epsilon i's are 0, right? So using this technique, I will find the value, the best value for beta 1 and beta naught, which gives me the minimum amount of error. Now, we know how to take the derivative of x square kind of thing, right? This is something's squared, right? But do you know how to take the derivative of something absolute? Because it becomes very easy for me to take the derivative of a squared quantity. Now, if I just take also this is going to be a partial derivative. So the partial derivative with respect to beta naught and beta 1 is very easy to take in this equation because it's a squared equation, right? So once we have those beta naught and beta 1 values, we will be able to find this line of best fit. Right. So now I have the derivation over here. Let's go over it quickly. So as we have already seen that my sum of squared errors comes out to be the sum of yi minus beta naught minus beta 1 xi whole square, because we want the sum of squares, square first and then the sum. So I've just taken the partial derivatives with respect to beta 1 first, as this 2 comes down, 2 times the sum of inner part remains same, yi minus beta naught minus beta 1 xi, and because of chain rule, beta 1 is the variable upon which we are taking the derivative, so xi comes out outwards, and to minimize it, I'm equating this to 0. Next, again doing the same thing for beta naught. I do not have any xi multiplied with beta naught, so I get 2 times sum of yi minus beta naught minus beta 1 xi equal to 0. So now I have got these two equations, right? Let me just open up the first equation. This 2 gets cancelled out. Sum of yi times xi minus beta naught times sum of xi, because this is a coefficient. This is just a number. It comes out outside. Minus comes outside. Minus beta 1, again a coefficient, times xi into xi squared equal to 0. Again the next equation, 2 times sum of yi minus beta naught minus beta 1 xi. I get sum of yi minus, because there is no ith value over here. This just this coefficient multiplied added up n times. So it's just n times beta naught negative over here minus beta 1 sum of xi equal to 0. Right? Let me just multiply it with xi on both sides. So what do I get? Sum of xi sum of yi minus n beta naught sum of xi minus beta 1 sum of xi whole square equal to 0, and this is my equation 2. Now just like we used to do in school, I multiply my first equation with n and subtract the second equation, right? So I get n sum of xi yi minus this value summation xi yi, then minus n times summation of xi square, n times summation of xi square. This gets cancelled out because when I multiply this with n, both of them, and there's a subtraction sign here, both of them gets cancelled out, and I get n plus n summation xi square plus this beta 1 is common for both, summation xi whole square. Now the difference here is, first I am doing the square, then summing up, and here it was sum of xi times sum of xi, so it becomes sum of xi whole square. So do not confuse them to be the same, they are different values, right? And when I just rearrange this equation to get beta 1 alone, I get n sum of xi yi minus sum of xi sub of yi. This goes that side and I get in the denominator n sum of xi square plus sum of xi whole square, right? Now just keep in mind that I can write sum of xi. What is the value of x bar? Very easily, I know that x bar is equal to 1 by n summation xi. This implies I can also write summation xi as n times x bar, and that's what I've done over here. One n is common, so nx bar, and then this was ny bar. One n came out as common, one remains over here. Same thing, this becomes nx bar times nx bar. This n is out common, then one n got out common and one remains. So if I cancel these both, I get my value of beta 1 estimate of the slope as sum of xi yi minus nx bar y bar divided by sum of xi whole square. Now first you are squaring, then doing the sum, minus nx bar square. Right? Now putting this beta 1 hat back into the second equation, I get sum of xi yi minus n beta naught sum of xi minus sum of xi whole square times beta 1 hat. Now I'll calculate this first, and then I'll put this value over here. That's why I've put on a hat. Hat means an estimate, right? So beta 1 hat over here equal to 0. Now I just rearrange the equation to get this value. Again, nx bar ny bar minus uh, n times x bar whole square, and then this n and this nx bar. N square gets out common, x bar also gets out common, gets cancelled out, and beta naught hat value I get as y bar minus x bar times the previously calculated using this equation beta 1. Now you see, we already have all these values in our sample data set, which we will always have with us, correct? So these values I will always have with me. Clear? So this is the basic fundamental of how a line gets fit. Now moving on to multiple linear regression model. In multiple linear regression model, what happens is these get calculated. Again, we do all of these things only. This is done for 2 beta naught and beta 1. There we get beta naught, beta 1, beta 2, beta 3, depending upon these variables that we had. Right? Do you remember we did a B, C, D, E kind of thing? Right now we just have um, some other intercept variable plus ax, something plus ax, right? But here we'll have all 5. So this is done using matrices, and this is best left for computers now that we have understood what the concept is really like, right? So MLRM, I'll just write the equation for you. So y equals to beta naught beta 1 x1 beta 2 x2 plus dot 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 beta p xp. So we have p variates over here and an intercept term. Also here I would now like to mention that there are some assumptions of a linear model, right? These assumptions you'll easily find in any books, and these are really important for us to check before applying any linear regression. Now after this, we'll just move on to our Python notebook to see how this can be done very easily using Python, right? So let us just go over the assumptions really quickly. Independence of observations. It means that, for example, if we have number of days over here, we should have these days independent of each other. We cannot be having some related values because we are calling them independent variables, right? These variables together are able to predict the y variables which are over here. So these observations need to be independent of each other. No hidden values. No hidden values basically means that it can't be the case that you do not have any value. For example, in this row, it can't be the case that you do not have any x5 value. You just have x1, x2, x3, x4. That is not allowed. You should have complete data with you. The x variables should be uncorrelated with each other. Now, obviously just see if x1, x2, x3, x4, and x5, these are, if they are correlated among each other, then what's the point of me keeping many variables together, right? These variables should be as different to each other as possible so that they add different kinds of values to my data, to my regression, right? If they are correlated with each other, what's the point of me, for example, if x1 and x2 are related with each other, right? Like here you might say that the temperature and the holiday season in India with respect to the summer holidays that children get in India, these might be related with each other, right? So it would be a good idea for me to check the correlation between x3 and x4 and then maybe get rid of one. I can check the correlation of both of them with the target variable, and the one which has the higher correlation, I can keep that and I can drop one of the variables, right? Also, it leads to, increase in the variance. We have not talked about variance over here. That becomes a little advanced, and this is just a, uh, you know, basic theoretical things, what all you need to know for an interview point of from an interview point of view, or if you're trying to do Python programming and if you want to read the parameters over there, right? If you see very carefully, there are a lot of parameters that you will find in linear regression model when you try to run it in a Python script, right? So this video aims to tell you all about that, right? But we'll not go into super detail of what variance of estimates are and what all those things are. But just understand that X variables should be uncorrelated with each other. A similar assumption is that the errors should be normally distributed, right? This also comes on at a later stage, but you can just treat it as an assumption when you are trying to um, do a project or something like that. Then, like we said, we are assuming a linear relationship among the x and y variables, because if we do not assume a linear relationship, then what's the point of doing a linear regression altogether? We might be doing a curvy linear regression, but that's just another story. In the assumptions of linear model, we have to assume that the relationship is linear. And last but not the least, that the error terms must have constant variance. Now, again, some of these assumptions are a little more harsh and require an advanced level of statistics to understand, so which is a little beyond the scope of today's video. So these are some of the assumptions that you need to take care of. So some of these things you just take my word for it. Just check the assumptions and then you can move forward. All right. There is one last thing that I wanted to discuss with you. That is an R squared value. Right? It is a very important topic. I promise this is the last topic and then we are moving quickly to the Python notebook. R square value basically is a score which tells us how good a model fit is, right? If I go a little bit deeper into R square, just like we saw sum of squares due to error, so it basically takes the ratio of explained variance in the model divided by the total variance, or explained sum of squares, or we could also write sum of squares due to regression divided by total sum of squares. So obviously this lies between 0 to 1, right? Higher R square value means that this is a better fit, which means that out of the total sum of squares, now this is not error sum of squares, this is total sum of squares, which is y minus y bar. Basically, how, if I just give you an example through a graph, if we come here, we see that there is some variation in between these points. We can obviously calculate variance for them. So how much of the variance can be explained by the addition of this x factor? If most of the variation can be explained by this x factor, obviously the R square value would rise. sum of squares due to regression line will rise divided by total sum of squares, right? So the more variance it can explain, the better becomes our model. So R square is a metric that can be used to judge how well a model is doing, right? So enough with the theory. Let's quickly move on to our Python session. All right, so let's start with the Python session of this video. So I'll quickly just go over it. So in Python, I have imported some of the basic libraries such as NumPy, Pandas, scikit-learn, which we'll be using for doing the actual uh, regression, matplotlib, and seaborn to be used later. We'll see if it's required or not, right? And I'm using the diabetes dataset, that is a pre-built dataset in the scikit-learn library, and so that you can also follow it at home. You don't have to download any values or something like that, right? So I have with me x and y values. Now since this is a very uh, friendly data set, it is just a practice data set, it can directly be created into x and y values. So you just need to write the command. First you need to import the dataset as from sklearn.datasets, import load underscore diabetes. Then x and y. Now y is going to be a single vector, obviously, because this is the target variable. And x, as I told you, could be x1, x2, x3, x4. We'll be doing an example of multiple linear regression over here, right? So we'll just do x comma y. So this will return, this load underscore diabetes will return two things. One, it will return a data set, data frame with only the x values, the independent variable, and the dependent variable y separately. So that is why I put a comma in between, and I've written load diabetes, return x, y equal to true, returning x and y data set separately. As frame means as a data frame, as a pandas data frame, right? So once I've done that, I can just quickly write a x dot head, and you can see that we have age, sex, BMI, average blood pressure, and these S1 through S6 are basically biomarkers of the blood. These are 6 different biomarkers which will help us predict the score of diabetes that we have. Okay, that is in the Y column. So if you see, Y has values 150, 175, 141, etc. By seeing Y dot head, and you can see that these are different values altogether. So these are only the x values, and these are only the y values. So this becomes my x1, x2, x3, x4, x5, x6, x7, x8, x9, and x10. So I have 10 variables over here and one target variable. So if I just write x dot columns, I can see these 10 variables. Now here comes the most interesting part. Just these 3 lines will fit your data set, right? So you just need to import the linear regression class from sklearn.linear underscore model. So from this module of sklearn, from the linear module of sklearn, I am importing the linear regression function. And then I create an instance of this class called LR. You can call this LR anything. See, the first line has to be written as it is. In the second line, if you're doing multiple regressions, you might write linear regression 1, linear regression 2, any name. This LR could be any name that you are giving, right? But what is this LR? This is an instance of linear regression. So I write linear regression, and in fit, I give x comma y. Now this x comma y is going to be this capital X and small y. If you have given some other names over here for x and y, you will have to give those different names for x and y over here. Right? And if you just hover over it, you can also see how the y values are looking. Correct? Then LR dot score gives you the R squared score. Right? If you just hover upon it, returns the coefficient of determination, R square. Right? So if you just run this, you get a 51.7% R square value, which is not super high. Like if the R square value is above 80%, then only we can say, as a rule of thumb, then only we can say that the regression is a very good fit. 51 to 52% is a moderate kind of a regression, right? Now, as we saw in the theoretical part, there is a beta naught, that is the intercept, and then you will have beta 1, beta 2 till beta 10, which are these variables. We will have the coefficients of these variables. So if I write LR dot intercept underscore, so this gives me the intercept value, and LR dot coef underscore, so these are 10 values, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So these are the 10 variable 10 values or the 10 coefficients for each of these. So in order to write an equation, I will write 152.13 minus 10.009 H minus 239.81 sex, 519.84 BMI plus 324.38 BP, and so on and so forth. Now you might be seeing that this sex value has been given as two values, 0.05 and minus 0.054. These are male and female values which have already been encoded in this fashion, right? It could be 1010 as well, but they have encoded this in this fashion. Now you might be interested in reading more about this data set, so feel free to go over the internet and try to research why this values have not been given as +1 or -1 or 0 or 1, and why these specific numbers have been given. I could give you a hint, and the hint is that if you see over here carefully, you might also see that BMI is never in second decimal places, 0 point and second decimal places, and negative also, right? So this could happen because many a times before doing regression, we as data scientists and data analysts are also doing standardization, right? Standardization means changing the scales of these values. Obviously, the age cannot be 0.03 or minus 0.001, right? So these are some kind of standardized values, and we might be seeing standardized values. What are standardized values in some other video, but you please feel free to go over Google and ask what standardization is. It's basically getting a range of values. For example, BMI, for example, age could be from 10 to suppose 60, so the range is 50, right? Sex is 0 and 1, just a small range, right? So in order for us to get similar ranges for all of these values, we do a standardization. That is why these numbers might look a little weird to us over here. And after we have done the prediction, because we have done standardization, we will later on de-standardize these values if you have done a standardization to get the real results. But as of now, we will be focusing only on the R square value and the intercept and coefficient, because that is the scope of it, right? So thank you so much for watching. I hope you enjoyed, and I hope to see you in the next one. Thank you so much.